Welcome to the 17th lecture of combinatorics. So, in the last class we were discussing about Turan's number, giving a lower bound for Turan's number. We will go back to that. So, this is the problem. We defined Turan's number as the smallest number of L element subsets of an n element set X, such that every k element subset of X contains at least one of these sets. Right? I was trying to give a picture using the bipartite graph. This is many times this is a very nice strategy to draw bipartite graphs when we are talking about set systems, and we can think about it, or at least we will get some clarity about what we are asking for, right. So, we told that we are we decided to take k element subsets of n on the right side. So, let us say this is A side and this is B side, and L element subsets n in this side. So, when I say n element subset, each n element subset is conceptually considered as a vertex of the bipartite graph now. And now between two vertices we inserted an edge, we put an edge. If this L element subset, say we will say A, and so maybe I can use S1 and this is some T1, so Si, and this is Tj. If Si is a subset equal to Tj, then I will put an edge between them. So, I will get a lot of edges here depending on, right. So, what we are interested in is in selecting certain subsets here, so certain vertices here, such that any vertex taken here has an edge into this set. It should not happen that there is a vertex here which has only edges. So, its edges are going to here, means any subset of this k element subset are not taken, no subset of this k element subset is not taken, right. So, that in some other what we say is that at least one of the k element subsets will have to be taken. So, you can see that here if you consider a k element subset here, how many edges will, so there is a vertex here of this thing, how many edges will go out of it. See, though I have drawn a big this thing, it should be considered as one vertex, because this is one k element subset which is thought of as a vertex of the bipartite graph. Now, how many edges will come out of this thing? Exactly k choose L edges will come out of it, right, because there are L possible L element subsets. What we want is, we are planning to select a few from this side. So, one of these k choose L things should be taken when I pick up this thing. So, if you are familiar with probability or something, probability, for instance, if I select, so there are n choose L of these things here, n choose L of members here in the A side, because there are L, the number of L subsets of n is n choose L. Now, if I pick up, so if I pick up a subset by tossing a coin, maybe which gives head with probability, say k choose L, right. So, 1 by k choose L. So, then it is like for each of this vertex here, each of this subset L element subset here, I may pick up that I will pick up in my collection with probability 1 by k choose L. So, if you are familiar with probability, otherwise you can discard what I am telling. So, then it looks like, so for if I do this thing for each of them, toss this coin for each of the n choose L members here. So, then I expect the expected number of set vertices I am planning I may take on this side is this, right. So, n choose L by k choose L, because 1 by k choose L is the probability of picking one of them, n choose L things are there out of that. So, then therefore, so you can expect that the expected number of vertices taken here, that means L element subsets picked up, it will be n choose L by k choose L, right. Now, so from this side, for each vertex I want, if here k element subset here, each vertex here means a k element subset. The way what we want is one of each subset, that k element subsets, L subsets if you consider, that should be picked up. So there are k choose L of them, because each one of those things are picked, the coin is tossed with probability 1 by k choose L. So we expect one of them to be in the set picked up, right. So therefore it makes sense in that sense, right. For instance, somehow we may be able to find one subset, but then of course, so this was an intuitive reasoning, I suppose, if you are vaguely aware of what is probability, and so approximately for instance how to randomly select things and things like that, and then that makes, so therefore this statement makes sense. So it's like if you had picked up n choose L by k choose L, of course at least that much you should pick up is what I is saying, of course here. So it's just because we expect, it does not mean that we should be able to hit, but what this theorem says is, suppose if you go below this thing, there is no chance, right. You have to take n choose L by k choose L, otherwise we do not have a chance of satisfying everybody. That means one of the neighbors of it will be picked up, right. That is what I say. So we need to take at least that much is what we think. Now we will do a counting argument and show that. So this is, of course, this was all intuitive argumentation, just to, of course this was not even an argument for this, to prove this theorem. It was just to give a feeling of what we are trying to do, right. What this quantity on the RHS is and what we really want, right. So what we want is this will also something like, you know, if you consider a k element subsets, we list down the k element subsets, right, for each of them. So we want a representative set such that every k element subset has a representative in our L element set. In fact, L, so for instance, if it was committees we were talking about, the k member committee is formed. So we should have at least L members in the committee, right. Or again we go back to our previous example, this red subsets are the subsets, right. For instance, as a committee we bribe this thing. So if that example does not work exactly here, but suppose you have to bribe each L element committee separately. Suppose I know these committee is fully bribed, this committee is fully bribed, right, or corrupted or something like that. Now I want for every k element committees here, I want one of the corrupted L set inside it. That is what we are saying, that is what we are trying. So approximately, so we want to show that k choose L by k choose L is a requirement, right, at least that much is required. Now to show this thing, what we do is, suppose some F family of L element subsets. So F is a family of L element subsets, is a family of L element subsets having the required property. So note that F is a subset of n choose L. So this is the notation for all the L element subsets of L subsets of n. Okay, is a subset of this, and now we want to show that cardinality of F is at least n choose L divided by K choose L. This is what we want to show, right. So now we will again use the double counting technique. So this time what we do is we index the rows by the members of F. Say let's say S1, S2, S3, these are all L element subsets, nullity of F. You look this coming from this, right, these are the members of F, right, these are the members of this, but these are all subsets again, L element subsets. Now this time we index the rows by the K element subsets T1, T2, T3, Tn choose K, all the K elements. Here in the columns we have n choose K columns because each K element subset has a corresponding column there, but there are not n choose, we do not have n choose L rows because we are only interested in the hypothetical the family we have constructed. So we claim that this family is one satisfying the property, right, and then we have listed the members here and we are interested in the cardinality of that family. And now again what will be the ijth entry? So S1 T1, here I will put a 1 if S1 is a subset of T1, otherwise I will put a 0. If S1 is a subset of T2, then I will put a 1 here, otherwise I will put a 0, like that, right. So similarly, so if I take an Si and a Tj, the 1 will be put if Si is a subset of Tj, subset equal to Tj. Not that these are all L element subset, L is less than equal to the cardinality of each subset corresponding to the columns because they are K element subsets, right. Now what are we interested in? We just count it in two different ways, namely we count the now ones, number of ones in the matrix row wise. So how many ones are there here, how many ones are there here. So as we told, we are R1, R2, so R cardinality of we will count. So that is easy to do, right, I equal to 1 to cardinality of. So we want to count the number of ones in each row. You can see that because this is an L element set, so a row corresponds to an L element set, we are asking in how many K element sets it is a subset of. I mean how many K element subsets are there such that it's a subset of. That will be the number of ones in it, right. So for each element you can easily see that for each L element subset the number of ones you see in the corresponding row will be same, though it will be in different places, that will be same. Why? Because it's the same number. So you give me an L element subset, right. Now I want to know how many Y's are there such that Y contains S. I will draw a picture like this. Suppose this is a Y, so now S has to be here, but this is already L. Now this total Y is K, alright. So now the question is we want to decide the remaining elements, namely K minus L elements of Y. In how many ways I can decide it, because these L things are already decided because that is exactly S, you fix it, right. Now we can decide this thing, but there are total n minus L remaining elements because the universe has L elements. We have already fixed the L elements corresponding to this S. Now the universe has n minus, so L remaining elements. Out of that we have to take this K minus L elements. So K minus L ways of picking it up, right. So this portion can be decided in n minus L choose K minus L. Is it clear? So because we want the K element subsets of the universe n element subset such that a given L element subset is there inside it. So the way to do it is you just pick up the members of that L element subset first and keep it aside, and now decide the remaining K minus L elements which should make up the K set, because this element subset, this L elements has to be there anyway, but the remaining K minus L elements can come from n minus L possible elements. Why n minus L? Because total number of elements in the universe were L, but this particular L elements we kept apart now, they are already gone, right? We cannot select again those things. So out of the n minus L remaining things, you have to select k minus L of them. So that is same for every L element subsets. So the number of ones you see in each row will be equal to n minus L, choose k minus L. So we can just write n minus L, choose k minus L here, right? But because this is the same number, we know this is equal to cardinality of f, because this is summation, same thing is summed up. So this is f into n minus L, choose k minus L. This is what our sigma Ri is, right? Sigma Ri is. Now this has to be equal to sigma Ci, the column sum. And what is that? The column sum says, so you pick up a particular k element subset, how many L element subsets are there inside it? That's what it says. I mean, how many L element subset does it contain from this f? You know, that is difficult to know. You know that suppose given a k element subset, given a k element subset, we definitely have k choose L element subsets inside it. K choose L element subsets inside it. Now k choose L element subsets are there inside it, of case. So there are k choose L element subsets inside it, but how many of them will come from f, that we are not sure, right? So but then let us say that, see, the column sum can be at most k choose L, that is clear, because you cannot have more than L element subsets, more than k choose L element subsets for a given k element subset. Even that much may not be there, because we are not considering all L element subsets as rows, only some L element subsets, namely that those L element subsets which are inside F are coming as rows. But we have no way of doing, because we do not know what that f is, right? We only have a hypothetical f there, so we do not have. So we just put an upper bound. We say that at most k choose L things are there. So the sigma Ci has to be at most this. So this is going from I equal to 1 to n choose k, right? Because there are n choose k possible k element subsets. So for each of them k choose L can be taken. This is what we get. And this is what I can do a little bit of manipulation here. K factorial by L factorial into k minus L factorial, and then here we have n factorial divided by k factorial into n minus k factorial. Now this will go away, right? So k choose L into n choose k is the row sum. So what do we get from here? So we get f, cardinality of f into, so in the previous case we have cardinality of f into n minus L choose k minus L, that is equal to, so we compare it, cardinality of f into n minus L choose k minus L, this is less than equal to, so right, because k choose L into k choose L into n choose k. This is what we get. Now, of course, so the question now is, so we get cardinality of f is less than equal to, so I just have to do the manipulation, k choose L into n choose k, k choose L into n choose k divided by n minus L choose k minus L, n minus L choose k minus L. So we will try it, so how it works out. So this is, of course I should not make any mistake. So this is k factorial divided by L factorial into k minus L factorial here, and numerator I am expanding, n factorial divided by n k factorial into n minus k factorial, and this total divided by, below this is n minus L factorial divided by k minus L factorial, n minus L minus k minus is n minus k factorial, n minus L minus k minus L, that is just n minus k factorial. So here what all things will cancel. So this n minus k, this n minus k and this n minus k factorial will go away, and this k minus L factorial and this k minus L factorial will go away, and of course see, you have to write it in a proper way. For instance, this into, maybe I can, if you want to do it, maybe I can do it more carefully here at least. So this will go away, at least that much we can be sure. So instead of doing this thing, let's say this will anyway go away, right? This and this will go away. So therefore I will write it again, once again, n here n factorial in the numerator, L factorial and then k minus L factorial and n minus k factorial in the denominator, n factorial divided by k L factorial, L factorial, n minus k minus L and n minus k factorial in the numerator, k minus L factorial and n minus k factorial in the denominator, right? N minus k. Here below we have the denominator goes up, that is k minus L and n minus k minus L factorial into n minus k factorial divided by n minus L factorial, right? Yeah, now we can cut this off. So what do we get? So finally we get n factorial divided by L factorial into n minus L factorial. This is what we get. That is n choose L. So finally what do we want to get? We have to get n choose L by k choose L, right? N choose L by k choose L. N choose L by k choose L. We get n choose L right. This manipulation is once again I will do. So this is correct. So the k choose L into n choose k here. So we have f into n minus L choose k minus L, right? And we want to show that f is less than equal to, sorry, f is sorry. So what I did is I made a mistake because we wanted to show a lower bound. I went for an upper bound. So therefore actually the thing is I took a lower bound here. In fact I have to take a lower bound here, right? So but this is not true here. So because this is only an upper bound, I took K choose cell into N choose cell, that is the possible thing. So therefore let me see, in the worst case we may have just one here, right. So we can write, yeah, that's one mistake I made. So sigma Ci, when I say sigma Ci, that is definitely less than equal to N choose K into K choose cell. But what we want to prove is that F is greater than or equal to something, right. But what we know is F into N minus L choose K minus L is the sum of rows. Now, so this is sum of columns also. So we want to get a lower bound for this, right, so that we will be able to say that F is greater than equal to whatever lower bound we get divided by this N minus L, this thing. So that's why I made a mistake. So therefore I want to get something here also, right. This is not good for me, right. So what can I do, but because I know that I have N choose K times, but the thing is I cannot say that for each column I have K choose cell entry once in it. That is definitely not true. For each column we may not have K choose cell entries, because why? Because go back to the matrix. Here if you consider the rows, we are on these rows only correspond to the members of F. So for instance, if I take a Tj, its subsets may be such that many of the subsets may be outside this, but one thing is sure, we have at least one subset in it, but that is the property of F. It is not that 0 subsets of Tj are listed here, no subset of Tj are listed here, because if no subset of Tj are listed here, then F is not the kind of family we wanted, because the kind of family we wanted was a family such that for every K element subset there is one of the L element subsets of it is part of the family. So definitely I am sure that at least one can be seen in this row. It is not that every member of this row will be zeros, right. So at least one will be seen from this thing, right. That is because F has that property, right. So therefore as a lower bound we can take just one. We do not know whether more than one element L element subset of this particular K element subsets will be listed here in the rows. That is not guaranteed, right. If it was if this F did not have that property, it can even be 0, but because F has the required property, we know that at least one will be seen. So we will just put 1 as a lower bound instead of here. So here where we have taken K minus L, here we will just put 1 into N choose K as a lower bound. So now it will so here we do not want this, we want greater than equal to, right, 1 into N choose K, this lower bound I will put. So 1 into N choose K, this just N choose K, right. So now okay, these manipulations were not what we were looking for, because this will only give an upper bound on F. Of course whatever we are getting as an upper bound for F is valid, but then the problem was, see, none of the manipulation that we have done is not wrong, but that was not our aim. Our aim, the theorem was asking for a lower bound for F, not for an upper bound for F, right. So because when we did this thing, what we got is this is N choose L, right. So finally upper bound of N choose L is quite valid but trivial, that is all. So this whatever, after doing all these manipulations, we had got this quantity, namely N choose L, but then it is like you have to take the F is at most all possible L element subsets is what it says, right, N choose L. So it is a trivial upper bound we got, but it is not wrong, because it is giving that information at least by doing this double counting. Or we will go by the because the non-trivial thing what we wanted was the lower bound. So we work on that part. So we get cardinality of F into N minus L choose K minus L is greater than equal to N choose K, right. So now we can do this thing. So cardinality of F is greater than equal to n choose k divided by n minus L choose k minus L. This is what he says. So, we want to show that this is equal to, so, still we are not through. Why? Because this is not, this is definitely true, but this what we want to show is that, again go back to that theorem, n minus L by k choose L is what we want to show, right. So we somehow want to show that this one is equal to n choose L by k choose L. This is what we want to show. Then it will work. So, we will work on that. So, n choose k divided by n minus L choose k minus L. We want to show that this is equal to n choose L divided by k choose L. Is this true? If this is true, we are done, right, because finally we got this thing from our double counting argument, and if we can show that this is same, then this is, we are done. But this, how do we show this thing? Let's try cross multiplying. It means, yeah, we will multiply this here and this here. So what is that saying? So that says n choose k into k choose L is equal to n choose L into n minus L choose k minus L. There are two ways to deal with this thing. One is just expand it and see. Of course, so n factorial divided by, this I am expanding, n choose k into k choose L, n factorial into k factorial into n minus k factorial, and here this is k choose L, k factorial by L factorial into k minus L factorial is on this side. I want to show whether I want to say whether this is equal to n choose L into n minus L choose k choose L. So, that is n factorial into L factorial into n minus L factorial into n minus L k choose L, right, n minus L factorial by k minus L factorial into n minus k factorial. So, when you minus n minus L minus k minus L, you will get n minus k factorial. So, all these things will cancel off, k factorial, k minus L, L factorial, n factorial, and n minus L. So, this is 1:1 thing. Just a blind checking by expanding both sides. So, therefore, it will, so note that there is no zeros and all we are cancelling, we just, even k equal to L case, this is a 0 factorial is 1 only. So, all factorials are being cancelled, therefore, no problem. So, this is 1 is 1, so 1 equal to 1, so it is true. Or if you want to get a combinatorial proof of that, we can try. So, what does it mean? So, this side n choose k into k choose L, yeah, n choose k into k choose L means, yeah, n choose k into k choose L. So, we have first selected a k element subset here, then we have selected an L element subset of it. So, let us say A is the k element subset, B is the n element subset. Then it is like we are counting A comma B's, pairs A comma B's, where A is a k element subset and B is an L element subset which is contained in A. We are counting these pairs A comma B's such that this is, for instance, this is the number of ways of selecting, this is the number of ways of selecting the first k element subset, and this is the number of ways of selecting an L element subset of that selected k element subset. So, this, the total thing n choose k into k choose L counts the number of pairs A comma B such that A is a k element subset of n and B is an L element subset of A, but this can be counted in a different way also. How? You could have first selected B, namely the L element subset. That can be done in n choose L ways, right. So, that can be done in n choose L ways, and after selecting B, you can fill in like we have done before the remaining, because you have already selected L thing. From the remaining n minus L elements of the universe, you could have selected any of the k minus L elements, so that you can make a k element subset it, right. So, that will be B is selected first, then A is selected, right. This will the again counting the pairs A comma B, such that B is an L element set and A is a k element subset of N, which is a superset of B, which is the same as saying that A is a k element subset and B is a subset of A, right. That will give you this thing. So, therefore, this and this are equal, n choose L into n minus L choose k minus L, both are same, right. So, here this also illustrates a usual counting strategy. The counting here we counted a pair of things, right. We counting pairs, triples, this kind of things usually happens in combinatorial arguments, and this tuple here the pair is interpreted in two different ways. First, as the first coordinate, the first member as the first selected thing, and B is selected after selecting that. Or then the other way is looking at B and then selecting B's first and then selecting A. This is also a kind of double counting, right. In double two ways we are doing it, right. So, therefore, we can see that. So, both the quantities are equal. We verified it in two different ways. First, by just putting in the equations. Second, by showing a combinatorial argument for that. Again, a double counting for that matter, right. So, the pair A comma B is counted in two different ways. Yeah, for instance, if you wanted like matrix kind of form for this formula, n choose k into n k choose L is equal to n choose L into k minus L, sorry, n minus L choose k minus L, right. So, we could have drawn it like this, draw a matrix, right. Then we list all the L element sets here. So, all L element sets, maybe you can say all k element sets are listed here, namely how many we are for total there will be n choose k of them, and similarly along the rows, all the rows corresponds to the L element set, as n choose L will be there. So, in principle we can write like this. So, that means the k element subsets are corresponding to the rows, we have k element subsets, corresponding to the columns we have L element subsets, corresponding to the columns we have L element subsets. Now, we can say that for the ijth entry here, this is the entry, the row corresponding to A, this is a row B corresponding. So, if B is contained in A, then we put a 1 here, almost the same strategy we did it in the earlier one, right. And then we count like that, we create a matrix, right. Whenever this particular the set L element subset corresponding to the column is contained in the set corresponding to the row, then we will put a 1 in it. Then now we are counting the total number of ones here, total number of ones here. So, how many ones are there? So, one way is to find the row sums and add up. That is clear, because a row sum will be there for a given, how many will be there, because given a k element subset there will be exactly n k choose L subsets, L element subsets of it. So, the row sum sigma rise here will be equal to n choose k into, because there are n choose k rows and each row contains k choose l ones, right. This is the row sum, and the column sum will be what? Column sum will be because there are n choose l columns, and here again for each column, that is an l element subset, we are asking how many k element subsets are there such that it is contained in that. As we have argued, it is n minus l choose k minus l, right. So this and this are equal. So that way, okay, we can again see it from the matrix as counting the number of ones in the matrix, that a comma b pairs we are counting, we told that correspond to 1 here, because this a correspond to a row, b correspond to a column, that is this pair a comma b, right. So okay, that was a different way of putting it. So we, but if it is like easier to think in terms of counting the number of ones in the matrix, we can always do it that way, right, of course. So or otherwise we can think in terms of counting certain pairs, right. So now, so we have proved it. So I just summarize that the Torrance number, we first explain what is this Torrance number, and then see, we wanted to get a lower bound for Torrance number in the process. So what we did is we made for the double counting, we made them rows and columns. The rows corresponds, so hypothetically assume that required family of subsets are known, and then we created a matrix for that such that each row corresponds to a subset, a L element subset, an L element subset from that family, and then each column correspond to any given k element subset. There are n choose k of them, there are n choose k columns. And of course initially I made a mistake of working for an upper bound by saying that okay, the row sum there was no problem, that was f into cardinality of f into n minus l choose k minus l, because each row contained exactly, we knew how many ones will be there, because given any k element subsets, it will be contained in n minus l choose k minus l k element sets. But the other way was not easy, because you know you don't have all the n choose l subsets listed as rows. So therefore because we don't even know what is this f, we just have a hypothetical property for that. So for an upper bound, we know that each column can contain only at most k choose l ones, because it's a k element subsets. How many l element subsets can at most be there? That's what I tried first. So that only led to an upper bound, and we saw that it led to a trivial upper bound. That was not useful, but still it illustrates the double counting argument anyway whatsoever. But lower bound, we need to get a lower bound for the number of ones in the columns. Of course it can be 0, of course, because given a k element subsets, what is it is just an arbitrary family of subsets you have taken for the rows, then it can be even 0. But in this case, this family had a property, namely that you take any k element subsets, at least one of its l element subsets will be in that family. That is why we know that there is at least one in it. So therefore if you add up the ones column wise, each column will contribute at least one. So the total sum, total number of ones will be at least the number of columns. So that is where we got n choose k. So we saw that the cardinality of that family into n minus l choose k minus l has to be greater than or equal to k choose l, sorry n choose k, and we divide it, and then we got a quantity, and the way we gave the lower bound was by another ratio, but we showed that that ratio is the same as this in the end. That again we used a double counting argument when we gave a combinatorial proof. This was the summary of this last proof. So there was a slight goof up in the presentation, but again it is not much of a problem. So and then next one we want to consider is, so I will quickly give another example of this double counting. It's again using this bipartite graph things, and also this is a very important topic, though I am not giving you the full proof. So this is the question we want to consider. So we have an n element universe, and then we have some family of subsets. So let us say these are the subsets. I am just writing it as S1, S2, S3, some Sn. So this is a family of subsets, right. So now, so that means some members of 1 to n will be here, 1 to n, some members of 1 to n will be here, some, these are all subsets of 1 to n. Now we want to select a representative from this thing, 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 and we should be able to say that this representative is for this set. He may belong to another thing, but for instance, these are all some say this is some groups of people, right. So it's possible that so for instance, these are people who can speak English, so these are people who can speak Hindi, these are people who can speak another language, so Tamil and so on. Now it's possible that one person can speak both English and Tamil, but so for instance, he is selected as a representative of English speaking people, then he should represent them, he should not help the other, right, other community, or maybe in any discussions he should represent entirely this English speaking. So we need distinct representatives for a thing. It does not matter whether the representative belongs to another community also, it does not matter, but we want a distinct one for each of them. Sometimes it is not possible, for that you can easily see. For instance, if there are too few people and too many sets, for instance, if we collect all the 2 raised to n subsets of it, so suppose S1, S2, S3, Sn, say we have S, this is S2 to the power, so why should I put n, so it can be m, right. So this m can be 2 to the power n, means all possible, 2 to the power n minus 1 if you want to remove the empty set, because empty subset anyway does not have any person, cannot get a representative for that. So now it is very clear that it is not possible, n is large enough, of course definitely 2 raised to n minus 1 will be greater than n, right, and there are only n people, and then one of them represents one, another one represents another one, and finally there will be still there will be sets which are not represented. So the question now is to know when can we have distinct representatives, right. This is what the Hall's theorem is concerned with. So Hall's theorem gives a condition, Hall's theorem gives a condition which gives, it is an if and only if condition, necessary and sufficient condition for like being able to, so that is a necessary and condition for the existence of distinct representatives for all sets, all subsets in the family, right. So we have put it as a distinct representative, like we have done in the last example. We can also see it as a problem in the bipartite graph. So this is, as I saw about set systems, it is nice always to see it as bipartite graph. See, sometimes it can be, you see in the last case we have an n all the n element subsets were, sorry, k element subsets were listed here, and l element subsets were, the inclusion was captured in an edge. Here what we can do is the universe itself, the members, the people, right, the members of the universe, they can be listed as say this is 1, 2, 3 up to n, right. This can be listed as the vertices of one side. The sets of the family, this is the family, so S1, S2, Sm can be listed as the other side. Now how will you so put the edges? If this member belongs to this set, then right, put edges. For instance, inclusion, for instance, if this not inclusion, so what is a membership? If for each element you can put an edge to a set if that element is a member of that set. Reversely also, for instance, if this particular set has an edge to this, if it contains it, this is a symmetric relation also. So these edges can be put like this. Now once you put these edges, so we have a graph, so it's a bipartite graph, right, and both sides of the bipartite graph represent something. So now what do we want? So we say that I want one person to be assigned to this thing, and one person to be assigned to this set, one person to be assigned to this thing, one person to be assigned to this thing, right. If some persons are not assigned to any, it does not matter. What I want is for each subset here in F, we need a distinct representative. So this person should not be, if he is assigned to this person should not be assigned to anybody else. This is called a perfect matching of this site. So okay, not perfect matching, sorry, this is called a matching of this set, this side, say this is A and this is B, a matching of A. This matching of A means every vertex of A is matched by that matching, right. So now the condition we want, the Hall's condition is concerned with giving a condition for the existence of such a matching, right. It need not, as we have explained, it need not happen. For instance, if M is too large compared to N, it will not be possible, right, because it will finish off one distinct representative, one representative given for this, one is given, finally after some time all the members here will finish off, and then it is not possible to give. So one, of course, that is a trivial condition, that we should have at least as many number of elements in the universe as there are sets, then only we can get distinct representatives. But is that enough? Even that may not be always valid. So if you, this essentially comes in the graph theory course, there is a very detailed discussion in graph theory books on this thing, or also the NPTEL course on graph theory also discusses this problem. So therefore we won't get into further details, but what I will just tell what the Hall's condition tells. So Hall's condition says, so this is A, this is B. Now if you take any subset of A, so you take a subset S of A, now you can see the neighbors of this S here. Neighbors of this means any member here which has an edge into this, right, and count the neighbors. So this is called N of S, usually number of neighbors. If number of neighbors is always greater than S for any set you take here, right, non-empty set you take here, if the number of neighbors is greater than equal to, even empty set is okay because that will be 0 greater than 0, greater than equal to S, then we say that the Hall's condition is met for this graph. Hall's condition is met for this, is satisfied for this bipartite graph. Means take any subset, there are 2 to the power S possible subsets you can take including the empty set. Then for each such subset, the number of neighbors N of S, cardinality of N of S, has to be at least the cardinality of the set itself. Then we say that the Hall's condition is satisfied. And Hall's theorem says that if the Hall's condition is satisfied, then it is possible to get a matching of A. We can get a distinct representative. In the terminology of the set system, for instance, if each vertex on the A side corresponded to a subset of the universe, then this condition, Hall's condition says, if you, for instance, for every subset, the neighbors are actually the members of it, right? You take the union of these subsets, for instance, this is S1, S2, S3, then you take S1 union, S2 union S3, that cardinality should be greater than or equal to 3, right? For instance here, so you can, so this is S1, S2, Sm, right? You can take say S10, S13, S16, S25, 4 subsets. Now if consider the union of S10, S13, S16 and S25. and find how many are there in the union, and there should be at least 4 of them. 4 correspond to 1, 2, this, there are 4 sets here, so at least 4 should be there. Then only the Hall's condition is met. Remember, in the bipartite setting, what happens is S10 is a vertex on the A side, and its neighbors are the members in it, the elements of it, right? And the neighbors of S13 are the the elements of S13, and similarly the neighbors of this vertex S13, S16 will be the elements of S16, and so on. Then you may wonder why. Suppose if each of them have one element at least, won't it add up to 4? Not necessarily, because it's possible that what S10 contains may be contained in S13 also. In fact, they can be same, right? Or maybe there are two, see for instance A and B are here, this can be A, this can be B, this can be another A, right? So A, B, C, so for this can be C. So everything together it's only A, B, C and C if you take the union, right? So we don't have 4 elements here. 4 sets does not guarantee that the union contains 4 elements. So the Hall's theorem says, but for any collection of subsets you take here, and if you take the union of it, and then you find the cardinality of the union, if it is at least the number of sets in that union, then the Hall's condition is met. And if the Hall's condition is met, you are guaranteed to have a matching of the A side. That means you are guaranteed to have a distinct representative system of distinct representatives, right? This is what I say. Now I am, see, of course one should ask, you need a proof for that. Of course you need a proof for that. That you should probably get it from some graph theory course or textbook. So I will not get into the details of the proof, but here I introduce these things. Of course this is an important thing, but I will not get into the proof of that, but rather I would think I will give one special case of it and show that the Hall's condition is met by doing a double counting argument, namely the case of K regular bipartite graph. K regular bipartite graphs. What is K regular bipartite graphs? So from the A side, the degree of each vertex is exactly K for everything. For every vertex on the A side, the degrees, and this side also it is K, this side also it is K. Now it is clear that yeah, so for instance we will start using the double counting argument to say that the trivial condition is met, namely, so if there are m sets here, there should be exactly m elements in the universe. Why? Because here we are adding up the degrees. I think it's time. I will continue in the next class.